In this video, we're going to look at section 10.4, which is polar coordinates. Now, we just dealt with parametric equations in sections 10.2 and 10.3. Now we're going to look at equations in a different way. So we're going to deal with polar coordinates here. Now, instead of giving us the left, right, up, down directions for getting to a various point, that's what rectangular coordinates do. They give you an X and a Y. And if you think about rectangular coordinates, it's telling you how far left, right you have to go. That's what the X value is doing. And it tells you how far up and down you have to go to reach that point. That's what the Y value is doing. So instead of giving it in that way, it's going to give us a distance, R, and a direction, which we call the angle theta. All right, that's again a Greek letter there, theta. So the polar coordinates are going to give us how far we went at what angle. Now, when I say at a certain angle, I mean from what we would normally call the x-axis. All right, so that in this case is called the polar axis, but it's normally what the x-axis usually is. So if we dealt with a typical point, let's say I dealt with the point, I don't know, 4, 2, that's the point right over here. Normally, in the rectangular form, it's going to tell me go 4 units to the right, 2 units up. I drew this really poorly. And in the polar form, we're going to say, well, we need to go at this angle from the x-axis, whatever that angle is, we'll call it theta, and we need to go this far, okay? So that's the idea of that. And by the way, notice that in the rectangular system, all of our directional lines are up and down and left and right. So we have horizontal and vertical direction lines. That's because in the rectangular coordinate system, we're telling us how far in the x direction we have to go and how far in the y direction we have to go. So that basically forces us to go left, right, up, down lines. In a polar system, well, the polar system, you'll often see graphs like this. So getting to the point, like I said, 4, 2, let's say in the x coordinates, it would say, well, let's go however many let's go at a certain angle. You can see the angles there. There's pi over 6, pi over 3. Let me zoom out just a bit. Pi over 2, it didn't do that very well. 2 pi over 3, etc., etc. So go at a certain angle, and then go how far ever many units out. Now, what we're going to end up doing is we're going to do a lot of converting back and forth between different systems. And when we do conversions back and forth between the rectangular and the polar system, then basically we're going to utilize a right triangle. And that's going to give us all we need as far as the information. I kind of sketched out a right triangle earlier on the graph, but we can do that in this way. So here's another version of that. So hopefully you remember back from some sort of a trig class that when you have a right triangle and you orient it like that, if we're focusing on this angle right here, this angle obeys the SOHCAHTOA property, which means that the sine of that angle is equal to the opposite over the hypotenuse, meaning the length of the opposite versus the length of the hypotenuse. The cosine of this angle is the length of the side adjacent divided by the length of the hypotenuse. And the tangent of that angle is the opposite over the adjacent. So let me say that again. We have three properties. Sine of the angle, usually again we call that angle theta. is equal to the opposite. I'm just going to say opposite divided by the hypotenuse. Hopefully, oops, dang it, I screwed that up. And then sine of the angle is adjacent over hypotenuse. And did I say sine? Cosine of the angle theta equals hypotenuse. And then tangent is opposite over adjacent. Let me write that down quick. Now, if we think about what this means as far as the polar coordinates go, maybe you've already seen this or figured this out. Well, think about that right triangle that we had before. So in that right triangle we had before, if I were dealing in terms of rectangular coordinates, x's and y's, and, excuse me, this angle, or at least this starting point here, was the origin over here, well, the adjacent would just be the x value. The opposite would just be the y value. And the hypotenuse, well, the hypotenuse is is the length that we would have gotten in our polar coordinates with our theta. So our hypotenuse is actually our r. Oof, I drew those pretty poorly, but you guys get the idea. So our adjacent, again, if this is the origin, if this point right there is the origin, and this is the point that I'm interested in, obviously we're thinking of this horizontal line segment as being along the x-axis or the polar axis, whichever system we're in. Then adjacent is x, opposite is y, hypotenuse is r. So if we go back up to our, let me erase that. If we go back up and put those things in, opposite over hypotenuse. Well, opposite, we just said, is the y value. The hypotenuse is the r value. Adjacent, well, that's the x value. Hypotenuse is the r value. So if I wanted to go from rectangular to polar, or polar from rectangular, I can think of this as y is simply equal to r times sine theta by multiplying both sides by r. So multiply this side, left hand side, by r. Multiply the right hand side by r. That gets rid of it on the bottom. You get y equals r sine theta. For the same reason, we have r cosine theta. R cosine theta would have to be equal to x. Now, tangent of theta, opposite, is y over x. So notice what this does. This says if I have r, I don't know why that's not in italicizing that, but if I have r and theta, then I can find my y by just taking r sine theta equals y. If I have r and theta, I can find my x by taking r cosine theta and setting it equal to x. Well, if I have x and y, I can find theta by this equation. And there is one last thing, is that if you think about this, well, this opposite adjacent hypotenuse also has to obey the Pythagorean theorem. So square this side plus square this side has to be the square of the hypotenuse. Well, what's that mean? Well, Pythagorean theorem would say x squared plus y squared is equal to r squared. So notice we have 4 identities that come out of this triangle. Those are the identities that we're going to utilize when we deal in terms of conversions. So whenever we're going to go from rectangular coordinates to polar coordinates, or from polar coordinates to rectangular coordinates, we have these 4 identities that we can use. Again, they all come from that one right triangle and 2 properties. The first property is SOHCAHTOA, that gives you this, this, and this. And the second property is the Pythagorean theorem, which gives you this one. So let's practice utilizing those conversions on, first off, points. So we're going to start with some polar points, and we're going to convert those to rectangular points. So we're given a polar point, we're given an r theta, and we want to come out with an xy. Now we have 4 different polar points here. So do each one separately. And if you would, go ahead and convert those polar points to rectangular points on your own using these conversions on the previous slide. Go ahead, push pause on the video, and try that. Hopefully you went ahead and did that. If you didn't, make sure you do that. So quite simple, 8 times 8 as your r value, pi over 2 as your theta value in polar coordinates means that the x value in your rectangular coordinates will be 8 times cosine pi over 2, and your y value will be 8 times sine pi over 2. Now, if you plug that into your calculator, by the way, make sure your calculator is in radians mode. If it's in degrees mode, everything's going to be thrown off. For always when we're dealing with polar coordinates, we're going to have our calculator set in radians mode. So we get 0, 8 as the rectangular point. Now, in the next problem, 4, negative 7 pi over 6, as the polar point, we're going to do the same thing, 4 times cosine of negative 7 pi over 6, 4 times sine negative 7 pi over 6. That leads to a point, the first point's a weird decimal. It's actually negative about 3.46 if I rounded it as your x value and 2 as your y value. Let me do a little bit making sure. There you go. And by the way, that a roughly negative 3.46, that's actually 2 times the square root of 3. Excuse me, negative 2 times the square root of 3, comma 2. Dang it. I am a little bit off here. So something's wrong there. But that's what that point is again there. Most of the times I'm not going to require you to memorize those what those decimals are or anything like that. Usually just round it to 2 spaces and that'll give you good enough. All right. Third point there, negative 8, 3 pi over 2. We end up, oddly, with 0, 8 once again. So we end up with a 0, 8 as our point in the rectangular coordinate system. And then the last point here is going to be 0, 0. So a couple things about these. Obviously, when we're dealing with rectangular points, when in doubt, you can always round it a couple decimal places. That's fine. But also notice that 2 different polar points gave me the same rectangular point. And you could surmise that anytime you have 0 as your r, no matter what value of your theta is, you get the origin, right? Because you didn't move up or down at all. So this is kind of a unique situation, and why you get this is because of how the unit circle works with polar equations. Let me go to a graph so we understand what I'm talking about. So let's take the polar graph. Now pi over 2 would be a 90-degree angle from the x-axis. It would be what we called the y-axis before. So if you're going to go 8 units out, let me scroll out till I get 8 units out. On the pi over 2 axis, you're going 8 units up, somewhere right about there. Okay. Well, what's pi over, excuse me, so pi over 2 is straight up. What is 3 pi over 2? Well, 3 pi over 2 is pointing straight down. And 3 pi over 2 pointing straight down, think about this. If 3 pi over 2 is the axis that's pointing straight down, then what does going negative 8 units mean? Well, it means going the opposite direction. Specifically, it means negative 8, we're going to go the opposite direction. So we're going to go up and end up there, which obviously is the same thing as going 8 units in the pi over 2 direction. Basically, we get this weird property that, if you add pi, you're going in the exact opposite directions. So negative, positive R values can both be used. All right, so there we go. Hopefully that makes sense. By the way, every time you go around and touch the x-axis again, you've rotated 2 pi radians. So if you did 2 pi plus pi over 2, that would be the exact same angle as just the regular pi over 2. Or if you did 4 pi plus pi over 2, that would be at the same angle as pi over 2 by itself. So there's lots and lots of different angles we can use there. For this reason, a lot of times people will often require angles to be from like 0 to 2 pi. Or sometimes people even force their angles to be from 0 to pi, or from negative pi over 2 to pi over 2, or something like that when converting. But for us, use whatever. Most of the time, we'll just go from 0 to 2 pi. All right, so that's how you convert polar to rectangular. I'd like you to go the opposite way now. I'd like you to convert rectangular to polar points in this case. And convert the following 1, 2, 3, 4 points. All right, so hopefully you went ahead and did that. Now let's start doing some conversions here, going from rectangular to polar coordinates. The rectangular point 2, 2, well, in order to find the r, we're going to use the Pythagorean theorem equation, r squared equals x squared plus y squared. X squared is obviously 2 squared is 4, 2 squared is 4, so you get 4 plus 4, that's 8. So r squared is 8, which means r has to be the square root of 8. Whoops. So the square root of 8 is what we get there. If you want to write that as 2 root 2, you can do that as well. In order to get the actual value of theta, you can do, well, the easy way on your calculator is to do the inverse tangent of y over x. So in this case, my y value is 2, my x value is 2. So we're going to do tan inverse on our calculator of 2 over 2. Now if you do that, I get a value of theta, which is about 0.7854, rounding it to 4 decimal places. That actually is the value pi over 4. So if you'd rather write pi over 4, if you don't recognize that as pi over 4, that's not a huge deal in this class, but it is a nice thing once you get used to it to recognize stuff like that. Pi over 4 is the actual angle. All right. Now, there is a slight weird thing with polar coordinates that we have to watch out for when we're using our calculator to find this angle of theta. And here's the deal. If you were dealing with the point -2, -2, in terms of R value, it's basically the same calculation. So the polar point is going to be, once again, R value square root of 8. Well, what's the theta? If I plugged in tangent theta, -2 over -2, well, in fact, you get the exact same value for theta. You get, once again, pi over 4. Now, we know that these 2 points are different, so their polar coordinates can't be the same. So something went wrong. And the thing that went wrong here is that these negatives cancel out. So your calculator can't tell the difference between negative over negative versus a positive over a positive. And that's the same thing with negative. If I had a -2 over +2, it can't recognize the difference between that versus 2 over -2. So what we have to do is we have to adjust this. Now there's 2 ways you can do it. You can either negate the R and say, well, whenever we're in the third quadrant, we're just going in the opposite direction. Or if you'd rather, you can add pi onto your angle. So let me explain what I'm doing there in, short term. So let me zoom in a little bit. So the point that we're trying to distinguish is the point 2, 2, which is somewhere in here, out there. Let me approximate it, somewhere in here, versus -2, 2. Oh, you know what? I gotta change that. I gotta scroll a little bit. There we go. 2, 2, -2, 2. Sorry. So 2, 2, somewhere in here. -2, -2, somewhere in here. Right, in terms of rectangular coordinates. I didn't draw it far enough, but that's okay. So obviously the line theta equals pi over 4. That pi over 4 is this line. So if I wanted to go out a certain spot, 2, 2, you could go in the positive direction, that square root of 8, or along the pi over 4 line. If I wanted to graph this point here, I could still be along this pi over 4 line, but I could have traveled negative square root of 8, so backwards square root of 8. Or what I could have done is I could have switched up my line and said, well, let's take this pi over 4, add pi to it, what that does is anytime you add pi to something, you're going in the exact opposite direction. And go a positive square root of 8 along the pi over 4 plus pi line. Either way is okay with me. I tend to utilize just the negative. So I tend to, when I write things down, just say, well, that's in the third quadrant, so we're going in the opposite direction. But again, you could have, instead of making the r negative, you could have kept the r as positive and added pi to your angle. Hopefully that's not too awful confusing. So with that knowledge, try the rest of these. Again, push pause on the video if you haven't already. If you've already done these, go ahead and move on to the next thing. You went ahead and did that. Now, let's take the rectangular point, negative 3, 4. Well, when you plug that into the r squared equation, r squared gives you a 25, and so r has to be either the positive or the negative 5. When you plug into the tangent equation, tangent of, again, it's always y over x. Well, I got a negative 0.9273. Now, I don't know exactly what angle that is, but I understand kind of where it's pointed. A negative 0.92, that's roughly negative 1 radians, almost negative 0.9 radians as we speak. So here's how I decide whether I should use a positive or a negative 5. I go to a graph and I say, well, negative means I've went down. That's what negative radians mean, about 1. So negative radians is somewhere in here. And where's negative 3, 4 at? Well, negative 3, 4 is way up here somewhere. Okay, let me scroll out a little bit. So negative 3, 4 is up in this region. It gave me a negative 1 radians, or negative 0.9 radians, which is down here, right? So what that means is I need to use the negative to get to negative 3, 4. I need to use the negative r value because I need to be traveling up and to the left to get to negative 3, 4. Hopefully that makes sense. So negative 3, 4, I need to choose up and to the left. That means I needed to use a negative 5. Okay? For the same reason, in this next one, we start with negative 1 square root of 3. It turns out if you square this and square that, add them together, you get 4. So r squared is equal to 4. That means your radius is going to be either a positive or a negative 2. Or I say radius, your r is going to be a positive or negative 2. And when I plug in tangent theta of root 3 over negative 1, I got a pi over 3, which is negative 1.047, blah, 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 blah. So I got a negative pi over 3. So let's decide which r I need to use. Do I need to use the positive 2 or the negative 2? So I go to a graph and I say, well, negative pi over 3. Negative pi over 3 is actually along this line here. That's negative pi over 3. So if my point is negative 1 root 3, now square root of 3 is like somewhere in here. So we're somewhere in here. This means that I need to be traveling in the opposite direction along the negative pi over 3 line. So I'm going to make my r be a negative. Hopefully that all makes sense. So we're going to make r be a negative 2, and there we go. Similar with 4, -2. 4, -2, you end up with negative 0.4636 as your theta, and square root of 20 as your r. If you go to your graph, negative 0.4636, I don't know, it's somewhere in there. 4 negative, oh, I didn't draw that very well at all. Let me erase that. Negative something like that, I don't know. 4, -2 is along that same direction. And so I need to be going a positive r in this situation. So do the positive r value. So we're going to use positive square root of 20 as my r. So that's how we convert from points in the rectangular system to points in the polar. You have to be really careful about whether you use the positive or the negative r. And again, your calculator always spits out thetas that are going to be between negative pi over 2 and positive pi over 2. So if your point happens to be in either the second or the third quadrant, you're going to have to use a negative r value. If your point happens to be in the first or the fourth quadrant, then you can use the positive r value with whatever you get out of your calculator. So hopefully that all makes sense. In the next video, we'll do equation to equation conversions, and we'll use the same conversion techniques.